Good morning, everybody. So before starting, I think last week we didn't introduce Veronica Martin, who will be here for a couple of months. She's working with Cristóbal and myself on some meteorological transport and networks within the new project. And the speaker today is Jean-Baptiste Delfort. He presented his PhD in Paris 7, and then he moved to, he worked on some diffusion and correlations of confined particles. Then he moved to Tokyo, to the laboratory of Professor Sano, where he did some work on Janus particles. And this is the topic of today. Now he's here since December, and he is working with Cristóbal and myself on directed particle systems. So this is fine.
Thank you for the introduction. So as Emilio just said, I've been here for 2 months, so I'm not going to talk about what I'm doing here. Instead, I'm going to talk about what I was doing during my first postdoc in Sano laboratory in Tokyo. And during my stay there, I basically did experiments on artificial swimmers called Janus particles here. And also I did some numerical simulations of this kind of self-propelling particles. So the reason to tell you about this today is because, first of all, the mechanism, the physical mechanism by which these swimmers can actually swim is interesting. It's called induced charge electroosmosis. And I will detail this later. And I think it's first interesting to explain how these particles can move and so on. And then I think it's a very convenient system when you want to study active matter, because you can actually control the motion of micrometer-sized particles. And there are not so many controllable systems of self-propelling objects of this size. And I will give you a few examples of studies that have been done using these Janus particles in the rest of my talk. So, okay. So my talk is in 2 parts. First, I want to tell you about the individual behavior of these particles. And I'm going to start by saying what they are. Okay? I think that's a good start. So I will describe the making process and the experimental setup. Then I will talk about this physical phenomenon I mentioned in the first place, induced charge electroosmosis. I will explain how this phenomenon can make the particles self-propel in a solution of water, and we'll see the kinds of motion that they can exhibit according to the control parameters. We'll find the equations of motion describing how they move, and finally, I will show you 2 examples of applications of these Janus particles. So the first example involves seeing if the fluctuation dissipation theorem can be valid for self-propelling objects of this size. And then we'll see that if we apply a feedback control of the trajectories of the particles, we can more or less control them and target them to a specified location in the sample, and even control their trajectories to a certain extent. Okay, so I will start by describing this famous particle. So initially we start, oh yeah, and I forgot to say, it will be a very experimental talk. Okay, so no numerical simulations here. Sorry. So,
thank you.
So first we start from polystyrene spheres of typically 3 microns of diameter. Okay? And what we do is that we put a droplet of this solution on a glass slide, and we let it dry, so that we get this kind of picture. And the most important point here is that you have to have a monolayer. Okay, so you don't want to have particles on top of each other. You need only 1 layer of particle. And the reason why is that after getting this glass slide with the polystyrene spheres, we put this in an evaporator. We heat some metal in such a way that we are going to coat a very thin layer of metal on top of the particles. Okay? So after this coating process, you get an object which is asymmetric. Okay, so it looks like this, and I think, yeah, you can see it on the picture that you have two different hemispheres, right? You have, on the top, you have a very thin layer of metal, and the bottom one is just bare polystyrene. And the thickness of this metal cap is really thin compared to the size of the particles. Typically, it's 10 nanometers, which is very small if you compare it to the diameter of 3 microns. And here, this is the best picture of a Janus particle I could find, but I'm sorry to say it's not mine. Our electronic microscope was not so good. So here they were using different materials. This is why you have SiO here and nickel here. In our case, we were using exactly the same process, but we are using polystyrene instead of silica. And instead of nickel, we are using chromium. Okay? So now, what do we do with these particles? So this is the experimental setup. It's very simple. You have two ITO glass slides. So ITO glass slides are just glass slides covered with a very thin layer of metal. So the advantage of this is that it remains transparent because the metal layer is only a few nanometers, so you can see through the glass, and at the same time it can conduct current. Okay? So if you put two slides in this configuration here with a spacer in between them, you can create a very small capacitor which is transparent, so you can see what's going on inside the capacitor. And so once we have this capacitor, we put a droplet of a suspension of Janus particles, and then we apply an electric field, which is an AC electric field. Okay, so it fluctuates, which means we have two control parameters. We can control the voltage of the electric field, and we can also control the frequency. And we'll see it's very important for the rest of the talk. And here you have a picture of the experimental setup. So you see it's extremely simple. You just have the two ITO glass slides here with the cable leading to a function generator, so that you can apply the electric field, and you look at the particles with a microscope. So what happens when you apply this electric field to the solution of Janus particles? So at first, as you have a dielectric material, it will get polarized, okay, like this. So you will have surface charges, even if your object is neutral. At first, you have positive and negative charges here. And at first, the field lines of the electric field will be perpendicular to the surface of the object. Also, as you have an ionic solution, the ions are submitted to a force because of the electric field, so you have a flow J in your solution. Then, as you have surface charges here, the ions of the solution are going to be attracted around the particle, and you have a screening cloud of counter-ions which will screen the electric charges at the surface of the particle. Okay? So this is this configuration here. And now, because the charges are screened, you recover the configuration with electric field lines which are now parallel to the surface of the object, like this. And these field lines will exert a force on the ions, so it will make the ions around the particle move, and in the end, the steady-state configuration you get is this one here, and now the curves are the streamlines. Okay, so at the end, with the ICEO mechanism, you get this quadrupolar flow around the particle. That's the general mechanism. If you have a homogeneous sphere or a homogeneous cylinder. But now,
sorry,
yeah.
I missed. You say you have a ionic solution. Did you say that? So it's not water. What do you have?
It's just water.
That's enough.
That's
the ions of the water.
Yeah, that's enough. Yes. But we also made experiments in which we were adding salts, like just NaCl, to the solution to change the concentration of ions. But most of the time, just pure water is enough.
Sorry, but those stream flows, those stream lines, sorry, do they show the flow of ions?
Yes, around the particles.
But that will depend on the sign of the ion. So
exactly, yeah. So you have opposite flows, actually.
So there will be flows in the both directions?
Yes. in this configuration, the electric field is here.
So the arrows are plotted, for instance, for the positive particles or whatever?
Sorry?
The arrows that appear there are only for the positive ions?
So in that case, it will be for the negative ones, because it's going down here, and this one would be for the positive ones. Okay.
There will be another flow.
There will be another flow?
Yeah, exactly.
No, but in the bottom, for instance, the other particles will also have a flow. The opposite one.
So here the negative charges will go down if the electric field is up like this. So this would be for the negative charges,
okay.
And the positive charges would be here. But here you will also have a flow of positive charges
Which will go
going in the other direction. Exactly. Yes?
I mean, in water, in pure water, I assume that the concentrations of iron is very, very low. So can it be that this works also with the dipoles? Because these water molecules are polar, so there is a reduction in dipole.
So, I mean, even if the concentration of ions is very small, you still have ions, and that's enough actually to make the particles move. I'm not sure I understood completely.
It's around, because it would be just so it's very, very, very small because it's the order of the ionic product of water.
Yeah, exactly.
So it works all the same.
But that's enough. Yeah. Then if you increase the concentration of ions, you can increase the velocity of the particles. So it depends also on the concentration of the water, but just pure water is enough to make it work. And in our case, this is ion exchange water, so it's even lower, actually. Okay. So what I just showed you is if you have a uniform particle, okay? Now, what happens if you have an asymmetric object like this? So when you apply the electric field, you have the polarization of the particle here, the screening cloud around it, and then you will have the steady state, the flow, the quadrupolar flow I just mentioned, which will appear around the particle like this. But now the difference is that you have two different hemispheres. So it means that you will have, in particular, more surface charges on this side, which is covered by a metal, than on this one here. And so in the end, the quadrupolar flow that you get is asymmetric. Okay, you have the particle interacts more with the fluid here than here, and this results in a self-propelling force, which will push the particle in a given direction. Okay. Another thing I want to say is that when you turn on the electric field, we always observe experimentally that this frontier here between the two different hemispheres, it always becomes parallel to the electric field. Okay, and actually, the ICEO theory, you can verify if you do a little bit of calculations that this is the only stable position you can have for the particle. There are two equilibrium positions, this one here, and the other one would be the other way around when it's perpendicular to the electric field. But this one is not stable. So our particles are always in this configuration here as soon as we turn on the electric field. And the last thing we observe is that there is an attraction between the bottom electrode and the particle, because you have positive charges here, negative here. So the particles always get very close to the bottom electrode as soon as you turn on the electric field. So in the end, you have a quasi-two-dimensional system. Okay, the particle will move in this plane here, and they will remain very close to the bottom electrode.
But
yes.
If it is an alternating electric field,
it doesn't change. It doesn't change anything actually, even if it's alternating. Yeah.
So what is negative and positive then?
So if the electric field were in the other direction, you would reverse the charges here and here, but still you would have a torque that would prevent the particle from rotating like this.
Yeah, but they will attach to the upper electrode.
No, because if you change this, you will change also the polarization of the particle here. So this electrode will become positive. Here you would have negative polarization. So you still have this attraction with the bottom electrode.
But why
don't you have a attraction to the top electricity just say you use Hunting force?
Sorry?
I don't understand why you don't have an equally strong attraction to the top.
You have one,
So
but you also have sedimentation, okay?
So it's a gravitational effect then?
Sorry?
So it's a gravitational effect then?
So there is a gravitational effect, but not only. You can clearly see, if you look at the particles with a microscope, that they get closer to the bottom electrode if you turn on the electric field.
Because they're already below.
Yeah, they are all, yeah, exactly. There is a joint effect of gravity and also. Okay. So the general picture of the particles in the solution is this one. So you have your dielectric, which is the polystyrene particle, okay, here, with a size A, which is the radius of the particle. On top of it, you have a coating, okay, which can be the metal part, for example. And then you have the screening cloud here. And the thickness of the screening cloud is generally given by the Debye length, which depends on the concentration of ions and everything, and also on the size of the particle. So generally, when you want to describe the configuration of this screening cloud, a lot of people are using the Stern model, which assumes that you have two different layers. You have a first layer here of ions, which is very compact. So the ions are very close to the particles, these ones, and they have a very low mobility. Okay? They are almost absorbed at the surface of the particle because of the strong electrostatic forces. And then you have a second layer, which is this diffuse layer here, where the concentration of ions is smaller. And these ones have a stronger mobility. Okay? So now, the idea is, can we describe how this screening cloud will appear around the particle when we turn on the electric field? So it was shown that if the Debye length here is small compared to the radius of the particle A, you can actually map this system here on a circuit with a resistance, which would play the role of the bulk of the ions in the bulk, and a capacitor, okay, here. And the idea of this capacitor is that at the frontier between the particles and the fluid, you have, for example, negative charges here, and just in front of them, you have positive charges, and they do not exchange because you have particles, charges inside and outside the particle. So the configuration is quite similar to a capacitor, a plain capacitor. So in our case, the situation is a little bit more complicated because we have one capacitor that would tell you that you have a screening cloud on one side and the particle on the other. But you also have to take into account this coating layer here. And this one actually also behaves as a capacitor. So if you want to describe this by a circuit, you have to consider two capacitors in series like this. One of them will play the role of the coating process here, of the coating layer, and the other one will play the role of the screening cloud. Okay? If you map the system on the circuit, then you can estimate the typical time it will take to charge the screening cloud and and screen what is the typical time you need to screen the surface charges of the particles. And this time is given in that configuration, by this expression here, where basically this parenthesis here is the total capacitance of the circuit, if you take into account the two capacitors here. And here, this 1 plus delta parameter is a rescale parameter, which is here because you have this double layer potential. Double layer screening cloud around the particle. So this tells you what is the time you need to screen the charges, and you can see that it depends basically on the dielectric constant of the solvent, which is here. The Debye length here, and this lambda p and epsilon p are basically the properties of this effective capacitor here. All right. So now we're going to use this charging time. So there is an IC, the theory of ICO has been written in this paper, okay, not by me. If you want to have more details, you can read it. Basically, you can calculate analytically what will be the velocity of a Janus particle doing three things. First, you need to find the boundary conditions for the slip velocity at the interface between the particles and the fluid. So you can do it by balancing on one side the electrostatic force, which is felt by the ions, and on the other side the Stokes drag force. If you do it, you find the Helmholtz-Smoluchowski boundary conditions, which basically tell you that the slip velocity is proportional to the parallel component of the electric field times the dielectric constant of the solvent. Here, eta is the viscosity, and zeta here is the zeta potential. And this potential basically tells you what is the difference of potential between the screening cloud and the ions in the bulk. And this is the next step consists in calculating this value here for a sphere of radius a. So I'm not going to give you all the details of the calculation, but if you have a fluctuating electric field with a coating layer and everything, this is what you find for the zeta potential. And then to get the velocity of the particle, you just need to inject this expression in the slip velocity and integrate the slip velocity on the whole surface of the particle. And if you do this, you find that the theoretical velocity for the particle should be given by this expression here. So here, omega is a very important parameter. This is the frequency of the electric field. Here you have the charging time we just calculated in the previous slide. Epsilon W is the electric constant of the solvent. Lambda D is the Debye length. And U0, yeah, and U0 is the typical induced charge electrophoresis velocity, which is proportional to the square of the amplitude of the electric field. Okay, so that's the theoretical result for induced charge electrophoresis. Now, can we apply this result to the Janus particles? In our case, we have two different hemispheres. Remember, we have one which is coated by a metal, and the second one which is just polystyrene. Okay? So what we do is that we use the previous result here in the two cases, and actually this factor here in the case of the metal will disappear, because in the case of the metal, the dielectric constant of the coating epsilon p is very high. It's almost infinite because you have the metal. So this goes to 0, and you can forget about this parenthesis. Okay? So you have a velocity for one side, a velocity for the other, and if you just take the difference, you have the total velocity of the particle. And here I plotted in red the first result here, which is the velocity of the metal side. Here you have the velocity of the polystyrene side, which is in blue, and which is opposite, of course. And then if you take the difference between these two quantities, you get the total velocity, theoretical velocity for the Janus particles, according to the frequency of the electric field, omega. Now, if we compare this theoretical result to the experimental measurements of the velocity of the particles, we find that it's in rather good agreement with the experiments. And there is no hysteresis. Okay? We have the same measures if we increase the frequency or if we decrease the frequency. I have to say, however, that here there are still two fitting parameters. The first one is delta here, and the second one is lambda p over epsilon p. And these parameters are the characteristic of the capacitors I mentioned in the previous slides. But the values we found are consistent with the dimensions of the system. So this is for the first control parameter, which is the frequency of the electric field. Now if you look at the amplitude of the electric field, E0, then it should be proportional to E0 square, because U0 is proportional to E0 square. And if you plot it for different frequencies of the electric field in semilog, indeed it is proportional to the square of the amplitude of the electric field. So the theory is working rather well in that case.
So the particles are oscillating in the alternating field.
No, they are not oscillating.
They move always in the same direction.
Yeah, because
when the field changes, still the flow goes in the direction of the
because even if you change, the interactions will always be stronger on this. Okay. So now, what is the effect of this asymmetric flow on the particles? So, if you apply a small frequency and a small voltage electric field, you have random walks. Okay, so basically it looks, okay, sorry, it looks like this. So you have a self-propelling force, which is pushing the particle in a given direction, and you also have rotational diffusion. Okay, so there is a given persistence length, which depends on the ratio between the self-propelling force and the rotational diffusion. So here you can see the particle goes in a given direction, and then rotational diffusion changes its orientation, so it changes also the direction of the particle. Okay. Now, what we noticed is that if you keep increasing the amplitude of the electric field or the frequency, you get a different behavior, which is this one. So for high amplitudes of the electric field or very high frequencies, instead of having random walks, you also have you have these rotations very regular like this. And the particles here, unfortunately, they all turn counterclockwise, but you can have both. It depends on the particles you are looking at.
Is this real time?
Yeah, this is real time.
And what is the frequency?
Here, I think it was 300 kilohertz.
It's much slower than the AC. This frequency is much slower than the applied frequency.
No, you mean the frequency of the rotation? No, the applied frequency is 300 kilohertz. And here, the real frequency is much smaller, but I don't remember the exact value.
So is this real time or not?
Yeah, this is real time.
It's 1 hertz.
Yeah, around that.
It's 1 hertz. It's much slower.
Yeah, I was talking about the frequency of the electric field. So why do you have this torque which makes the particle rotate? So up to now, I've been showing you this picture of the Janus particle, which is of course an ideal picture. But if you look at them with an electronic microscope, you can maybe see here, even if the picture is very small, that the interface between the two sides is not perfectly straight, of course, because the coating process is not perfect. So in reality, you have something more like this. Okay. So what this means is that you can have not only this breaking of symmetry with two different hemispheres on the left and on the right, but the quantity of metal can also be, for example, more important on the top hemisphere than it is on the bottom one. If you have this configuration, then it means that the flow on one side might be more important than on the other side. So you have not only a self-propelling force, but also a torque which will make the particle rotate. Okay? So then, can we describe the motion of the particles, assuming that we have a constant force, self-propelling force F, and a constant torque applied on the particles? So if this is your assumption, you can write a very simple system of Langevin equations. Okay? So here, phi is the angle of the orientation of the particle, and r is its position vector. So the position vector is submitted to translational noise, mu of r here, which is a white Gaussian noise, and the angle of the particle is submitted to rotational diffusion. So you have this mu phi, which is also a white Gaussian noise, and you have this constant force in the direction of the orientation of the particle u, which is the orientation vector, and you have this constant torque m, right? And these two mu here are the typical properties of white Gaussian noises. So you can actually solve that thing, and you can calculate, for example, the mean square displacement, and then we'll compare the theoretical result here to what we find experimentally speaking. Okay? If you believe this theory, then the typical rotational frequency should depend only on the torque m, okay, and also on the rotational diffusion coefficient here, and on the thermal energy. On the other hand, the velocity of the particle, the average velocity, should only depend on the self-propelling force F. So, okay, so let's see if we plot this thing. We're going to go step by step, okay? At first, if you have no electric field, you have no self-propelling force, you have no torque acting on the particle, so you recover that the mean square displacement should be linear, and this is indeed what we find experimentally, okay? Now, if you turn on the electric field, but for example, a low voltage, in that case, you have a self-propelling force, and you also have a torque, but the torque will be rather small compared to the typical thermal energy. So you can neglect this guy here, and you get this simplified result for the mean square displacement. And once again, if you compare this to the experimental values, it works rather well. And finally, you can take the full expression if you have both. And this is the expression I showed you in the previous slide. And in that case, you can see that the mean square displacement is fluctuating. And once again, we can fit rather well the experimental values by the analytical expression. There is always a discrepancy at small times, but I think it's because of the pixelization of the image. Basically, the size of one pixel is comparable to the value of the mean square displacement, so you always overestimate it for short times. We need a better camera. Okay. So now I want to show you two examples of how you can use these Janus particles to study active matter, and for example, analytical properties. So the first study has been done by Suzuki, who is the first person who worked on these Janus particles in Sanolab. And so what we wanted to do was to check the validity of the fluctuation dissipation theorem for particles of a micrometer which are self-propelling. So what he did is that he considered this kind of configuration. Sometimes the particles are stuck to each other. Okay? In some configuration, for some control parameters, you can have an attractive force between the particles. And also, unfortunately, sometimes they stick to the bottom electrode. So if you're lucky, you can have this configuration in which you have one particle which is stuck to the bottom electrode, so it doesn't move, and another one which is stuck to the first particle. And this one is still submitted to a self-propelling force, okay? So it will rotate around this one, like this. Okay? So if you want to describe this particle, you can write this equation of motion here. And in that case, tau here is the torque acting on the self-propelling particle. And the idea is that you can actually estimate this torque here with two different methods. The first one is to use the fluctuation dissipation theorem. If you do it, you can find this analytical result, which tells you basically that if you have the distribution of the delta theta, which is the angle of this particle, you can relate it to the value of the torque here. So if you measure these distributions, you can find a first estimate of the torque. But you can also find, calculate what should be the torque according to the Stokes drag force. In that case, the torque should be given by this Stokes drag force times d, which is the diameter of the particles. And the Stokes drag force depends on the viscosity of the fluid eta. R here is the radius of the doublet, so it's 2 times d. And v here is the rotational velocity of the particle. So you can measure v. And beta here is a parameter you have to take into account because your particle is next to a surface. So the Stokes force is slightly modified. Okay.
So the beta here is not a temperature.
No. Beta is the parameter. it rescales the Stokes drag force, and you can calculate it using facts and law. So it depends on the diameter of the particle. Yeah, only on the diameter. So here is the distribution of the delta theta angles that you get for different amplitudes of the electric field. So you get these distributions here. And then you can plot this left quantity here according to delta theta over kBt. And you find that for a given amplitude of the electric field, all the data points collapse on one straight line. So for example, for the blue ones, you have roughly one line here. And the theory tells you that the slope of this line is the torque which is applied on the particle. So from here, you can estimate the value of the torque, and you find that it's proportional to the square of the amplitude of the electric field, as is the self-propelling force. So this is consistent. Then you can compare these values here to the ones you could find using the Stokes drag force, which are in blue here. And you find basically the same thing. So what this tells you is that in that case, you have a good validation of the fluctuation-dissipation theorem, as the two measures are in good agreement. And actually, this fluctuation-dissipation theorem has been used by a lot in biophysics. People especially try to measure for the ATPase 1 protein, what was the force that this protein exerts on other molecules. And they use this fluctuation-dissipation theorem. So it's nice to have a validation of it. Okay, so this is the first example. The second one involves how can you control the motion of the Janus particles. So the idea is that if you want to send this guy here to a specific target location, for example here, if you apply an electric field and that you have random walks, you cannot control the motion of this particle. It will just go randomly in the sample. But if you switch in a clever way between rotations and random walks, you can actually send this guy wherever you want to. So the idea is that if the orientation of the particle is not the one you want, for example here it's a bit straight, you would like the orientation to be in this direction. So at first, what you do is that you apply an electric field which will induce rotations of the particles. So your particle starts rotating like this, and at some point, you will get the right orientation vector. So when you are in this configuration, then you change the electric field in such a way that now the particle will random moves. So it will go straight on with a given persistence length, and so it can reach the target location. So we were wondering if by using this feedback control process, we could control the trajectories or send the particles wherever we want to. So we wrote a LabVIEW program, and so here we are controlling this particle. So the idea is that here we are trying to write a UT for University of Tokyo. Okay, that's incorporating. Okay. So what the feedback program is doing is that at each moment we are tracking this particle here, and we calculate its instant velocity, and we assume that the velocity of the particle is the same as its orientation. So then, if the orientation is good, we apply a small frequency electric field of 5 kilohertz, which makes the particle go straight on. Okay, you have random walks. And then, if the orientation is not good, we increase the frequency of the electric field so that it starts rotating. And once it has the good orientation, we switch back to the low frequency electric field. And by doing this, we can more or less control the trajectory. So you have to have a little bit of imagination here, okay? But if I show you the end of the movie, you can more or less recognize UT. So of course it's not perfect, especially because when we change the orientation, you have these small loops here. So So, but if you cross going the trajectory or whatever.
But it's remarkable, they are Japanese particles writing in Latin letters.
Yeah. But I have another movie which is very Japanese for the end. Okay. Yeah, so to come back on this system, so I'm not an expert in information theory or anything, but it could be interesting to see if we can, because as you have the feedback control process, it kind of make me think about Maxwell demons. So is it possible to measure quantities like, I don't know, the Shannon entropy, for example, in this system, to test generalized second laws of thermodynamics? Well, I'm not an expert, but if you have some suggestions, I think it could be interesting. Right, so I will finish with the collective behavior of the particles. And this collective behavior depends on the frequency of the electric field. And we have three different kinds of behaviors that I will show you. So here you have the frequency omega. At small frequencies, what you see is that if you have a suspension of particles, you get these aggregates of particles. So they are forming clusters. If you increase the frequency, the particles start moving, and you have a rather homogeneous solution. Okay, this is what you have for frequencies below typically 30 kilohertz. Okay. And then if you increase further the frequency, then you have a completely different behavior, like this. So for high frequencies, you have attractive interactions between the particles. So you have some kind of phase separation of the system, where you have dense dynamical clusters here, which are separated by a dilute phase of the particles.
Why do you have attractive interactions?
I'm going to explain it in a couple of slides.
And the clusters for large frequencies and low frequencies are the same? Or is it different?
I don't really know, actually. In theory, the size of the clusters should increase when you increase the frequency.
I mean that interaction, well, maybe you are going to explain that. So it's the same interaction for low frequencies and for large frequencies, or is it different?
No, you have different interactions.
Different
and this is what I'm going to explain now, actually. So let's start with the first region here, which is the aggregation region here. So if you have a very low frequency of electric field, what happens is that you have time to completely charge the screening cloud of ions around the particle. So all the surface charges are screened, which means that basically the asymmetry between the two sides does not matter anymore, okay? Because anyway, the surface charges are screened. So in that region here, the particles do not move, okay? Well, they move, but because of diffusion. You don't have the self-propelling force. And the reason why they are aggregating like this is because of the electrophoresis. So if you put a neutral object in an electric field, which is uniform, you end up with something like this. So you have a polarization of the object, okay? But if you calculate the integral of the force acting on the object, you find 0, because the uniform. So this guy here doesn't move, okay? But then if you have a non-uniform electric field, in that case, if you calculate the integral of the force, you will find that it's not 0 because of this non-uniform properties of the electric field. And the electrophoresis tells you that an object which is neutral in a non-uniform electric field will always go to the places where you have the highest electric field. Okay? So then, if you have a Janus particle which is completely screened, this particle will deform the electric field lines, okay? Which means that locally around this particle, you have a zone of high electric field. And that's why you have this aggregation behavior, because the other particles are attracted by this zone of high electric field. And this results in the aggregation I showed you on the first picture, which is here. And if you check at the orientation of the particles in the cluster, you find that it's completely random. Okay, so you don't have like the gold hemisphere attracted by the other one. Okay, here the orientation of the particle doesn't matter. Then, if you increase the frequency of the electric field, you enter this this kind of collective behavior. And here, what's happening is that, so you have ions, screening clouds around the particle, but you don't have time to fully charge it, okay? So in the end, all the charges, the surface charges of the particles are not screened, and you are in this configuration, which means that you have only positive charge, negative charges on top and positive ones on the bottom. So in this configuration, you have dipolar repulsive interactions between the particles. And this is why you have this homogeneous suspension of particles. Okay? And finally, here.
Excuse me, but in that case,
yeah.
if it rotates, it will attack.
Yeah, but you cannot make it rotate because of the
Because of
flow.
the electric field.
So it's always in this configuration.
Okay.
But in the last region here, when you for high frequencies, what happens is that you have an interesting transition from a dipole to a quadrupole. So basically, if you want to calculate the dipole moment of a given dielectric, you can say that it's proportional to the electric field times some kind of effective polarizability, which is this thing here. And the effective polarizability depends on the Clausius-Mozotti factor, which you can express according to the complex dielectric constant of the particle and the solvent. Okay? So the thing is, if you use the values of the polystyrene and you calculate this guy, the Clausius-Mozotti factor, and you plot it according to omega, which is the frequency of the electric field, what you find is that this thing becomes negative for a critical frequency, which is around 60 kilohertz for the polystyrene. For the metal side, the electric constant is very high, so it's not very sensitive to the frequency of the electric field. So what it means is that you are going to reverse the dipole moment of the polystyrene side if you go to high frequencies, because there will be a lag between the switch of the electric field and of the dipole of the polystyrene side, which cannot follow because it goes too fast, basically. So you end up in this configuration here. You reverse the polarizability of the polystyrene side. And so in the end, the particles are in this configuration. So you still have some counter-ions around it. But this time, if you look at the different hemispheres, you can see that now they have an attractive interaction. So the same hemispheres will have repulsive interactions, and the opposite hemispheres will have attractive interactions. And this is why you have the formation of clusters like this. And if you work on dilute suspension, because you have these patchy interactions, you have chains like this, which appear in the sample. And these chains have a very funny motion. I can show you. So here there is no electric field. Okay, so you just have diffusion of the particles. And at some point, we are going here to apply an electric field with a high frequency to induce the self-propelling motion and the patchy interactions. What you can see is that you have like this motion of particles, of chains of particles. And they have a very complex motion which depends on their size, on their shape, and everything. Yeah. And you can see that at some point, the particles are sticking on the bottom electrode. This is because of this attraction between the bottom electrode and the particles. And that's very a problem for our experiments. You cannot experiment for such a long time because eventually everything will stick on the bottom electrode. So you have to do it again and again. I could watch this for hours.
The particles warm up as they run, so when you
Sorry?
So the particles dissipate heat when you put the electric fields?
Not really, because the electric field changes. I think at first...
There are some currents in the metal.
Sorry?
There are currents in the metal, so probably they heat up a little bit.
Yeah, but it's not really, well, we cannot really see the difference here. I mean, it doesn't change the interactions or anything. You have other types of Janus particle which can move by thermophoresis. So the idea is you use the same object, but you shine a laser on the particle, and the way the particle captures the photons depends on the side. So you have a gradient of temperature, and because of that you have thermophoresis. That's another kind of self-propelling motion of Janus particle. Okay, so I'm going to end my talk here. The take-home message is the following. Janus particles are asymmetric self-propelling colloids. They are moving because of a phenomenon which is called induced charge electrophoresis, which induces both a self-propelling force and also, in some for some control parameters, a torque. Okay, so you can have rotations or random walks. And by tuning the control parameters, you can control the velocity of the particles, their direction of propagation, their type of motion, and also the interactions to a certain extent. And here you have like a sakura flower, which is a cherry blossom flower, which is one of my colleagues did using the Janus particle. So this is a Japanese movie I was telling you about. Yeah, and to finish my talk, I would like to acknowledge the people I've been working with. So Sano Laboratory, of course, a very international laboratory, as you can see. Dr. Ryo Suzuki, who is the first who was working with Janus particle and who did a great part of this work. Tomoyuki Mano, who is a student who worked on the feedback control program. And also John Molina, who is from the University of Kyoto and who helped me a lot with especially the numerical simulations. Yeah, so thank you for your attention.
Questions? Comments?
Yes. What's the real world application of those Janus particles?
Do you mean by real? You mean industrial? So, a lot of people have been trying to control motion of micrometer objects, for example, for medical applications. Here we are very far from the medical applications. That's really the beginning. But I think the concept of switching between two different kinds of motion to control the motion of a given particle can be interesting. I think here it's more interesting for out of equilibrium physics studies. Like as I was saying, if you want to, for example, test the second law of thermodynamics with information theory or that kind of things, I think it can help because it's really controllable. And you have very few systems of self-propelling objects so controllable at this size. There were also a lot of experiments with bacteria. The problem is that it's much more complex because you have to take into account chemotaxis, for example. Here we don't have this problem. We just have hydrodynamic, steric, and electrostatic interactions, and we more or less understand them. So I think it's a good model to study active matter.
And you mentioned also biomedical application of the ATP molecule.
So what I was saying is that a lot of people are trying to, that's when I was talking about the fluctuation dissipation theorem. Yeah. So recently a lot of people in biophysics try to measure what is the force one protein, for example, can exert on another one. And this kind of thermodynamic quantities at a very small scale. So they were using like fluctuation dissipation theorems and this kind of tools. I think it can be interesting to compare with Janus particles because this is rather simple, and as I said, we can control them. So we can check, for example, validity of the fluctuation dissipation theorem. I think it's more interesting for theoretical physics, actually. More real applications.
Nanomaterials, or there is no applications? I don't know, I have no idea.
Yeah, there are many people trying to study the physics of suspensions of active matter. For example, Kate's group in Edinburgh is really interested in this. Yeah, that could be also interesting to compare with Janus particle.
Questions? Maxi?
Can you think of a situation in which you have one kind of particles having the motion in one direction and others in an opposite direction?
I think if you have the same particles, no, because in that case the frequency for which, yeah, but you can make if you try with Janus particles of a different size, for example, or if you use different materials. For example, if you use particles made from silica and polystyrene, then the switching frequency should be different. So in that case, you could imagine that some particles will go in one direction and the others in the other direction.
And could you think of doing experiments with that thing on crowd motion?
Crowd motion, you mean directional motion, for example?
Crowds of things moving in one direction with...
Yeah, so I spent half of my postdoc working on directional motion of the particles. So here it doesn't happen, and basically we've found that considering the hydrodynamic interactions between the Janus particles, the floating state in which all the particles are moving in the same direction is unstable. They have an instability which comes from the far-field hydrodynamic interactions. You cannot have this directional motion for this kind of particles, unfortunately.
There is work from Vaderian and also from Lowen, where they have this kind of, let's say, this competition. So colloids going in one direction, colloids going in the other direction, So there was an article in Nature, I think, I will later.
But it's for Janus particles? Or
I think so.
Many questions. Ingo was first.
Maybe I missed that point. How about charge neutrality of the Janus particles? Is that always kept?
Yeah, they're always neutral. You have the polarization, but the total number of charges.
They come in contact with the electron.
Yeah, that's a good question, but I have an interesting argument. So, for us, when they come in contact with the bottom electrode, that's not good because they are stuck generally. So we use polymers to coat the bottom electrode, like twin 20, for example, to prevent them from sticking. So I don't think they are touching it directly. And when they do, generally, they stop completely. So I guess in general, they are neutral. Then can they touch and then detach and then be charged? Maybe it happens, but we didn't see anything that would indicate it in the experiments.
Domenico?
Yeah, I know of Janus particles who, like for chemical gradients, so they are coated on one side with a catalyst, say they activate the reaction and they form a chemical gradient.
Yeah.
So, and I've been, seeing a few talks on this subject, and if I don't remember wrongly, there is some swarming motion, but directional swarming motion in these cases, if my memory was fine. So I was wondering, like, if somehow you observe different motions with respect to that case, because physics is quite different, like it's always Janus particles.
Yeah, so I know these particles, they are made, they have one side with platinum, I think, and you put them in oxygenized water or something.
Yeah.
So the catalyst, there is a catalyst, catalytic reaction, and so they move in a given direction. If I remember well, they have attractive interactions. At least the article I know mentioned attractive interaction, and they have phase separation in that case. So you get clusters of particles, a bit like what I showed you in one slide. It would be yeah, it would be this. It looks like this collective behavior. I don't know any kind of Janus particles exhibiting directional motion, which means that they are all moving together in the same direction. But in theory, this is possible because it depends on the self-propelling mechanism. Okay. With this self-propelling mechanism, I won't go into details, but with this self-propelling mechanism, you have this instability I was mentioning, so you cannot see this directional motion. If the particles move in a different way, then directional motion could be observed. But I don't know exactly. I haven't studied the platinum Janus particles you're mentioning. So, to my knowledge, they are only exhibiting clustering. Directional motion.
I don't know. I would honestly go and look a little bit more because if I don't remember, if I remember correctly, I remember this kind of cluster motion. They move all together.
Ah, a cluster motion.
Yes, cluster, not
okay.
Single particle motion,
okay,
but
okay.
Directional motion of the cluster.
Okay.
It was easier to control because.
That's possible, but there's a difference between motion of a cluster and synchronization of individual motion of all the particles.
No, it was cluster motion.
Yeah, okay. So yeah, that might be possible.
Another question?
You mentioned the influence of asymmetries.
Yes.
In the Janus particles. Do some people also try to take profit from special coatings which are deliberately anisotropic?
You have many kinds of Janus particles. You also have catalytic rods with two different sides, but with a higher aspect ratio. Some people designed I think some kind of Janus particles like this. So then you have a torque because the particle is clearly anisotropic, so then the particles are rotating like this. There are many kinds of Janus particles.
Okay, last question.
How does the phenomena that you have described, how does it depend on the size of the particles? I mean, in principle, forgetting about how would I do that experimentally, if these particles were much larger or much smaller, would it make any difference?
So in theory, when the particle is much larger, you have higher velocities. And we checked this experimentally, and it works. The problem is that the attraction between the particle and the bottom electrode also increases when you increase the size of the particles. So if you take two big particles, they are stuck very quickly. But the theory I introduced also works for different sizes. 3 microns is the size which is the most convenient for the experiments because the particles have a good self-propelling motion and they do not stick too much. But you can.
I mean, just dreaming, if you were in the other direction, if you were to nano size, would that make any?
To nano size.
I mean, in which sense does this scale with the diameter?
I have no idea. I think there are some nanometric asymmetric particles, but I didn't read the
mechanism important.
Yeah, well, I don't know what will happen. I think you can make them.
Okay, we should stop here and thanks.